Beyond. Hello, everybody. My name is Kevin Kotchek. I'm the founder and CEO of ChemicalQDevice, here to tell you about it's basically a big pitch deck supporting information, growth potential, and additional supplementary information. This is quantum medical and business. So if you've been following the news, especially medical, some good news I'll get to. So the problem is, so this is a traditional pitch deck. The problem is that the medical field has not yet significantly experienced quantum and classical hybrid advantage. Now, conventional computing lacks specific parallel and exponential processing benefits observed in quantum mechanics. And in specific, current Alzheimer's disease AI ML predictions don't yet fully take advantage of quantum algorithms on quantum computers, and therefore user satisfaction is limited to deep learning increases. So bullet point 3, AI, ML, MRI, and PET neuroimaging results are not substantially based on quantum computing and sensing combinations. And currently they're limited in sensitivity, signal to noise ratio, and resolution. Now, the solution with this is basically quantum machine learning. Now, quantum machine learning is a very broad field. It's the most common application, say, for instance, with quantum computing, and it's QML in specific is suitable for medical big data. So you'll hear these things like the quantum computer isn't, but QML, which is a hybrid approach with classical, is. And in specific, Los Alamos National Laboratory says that sample complexity is likely a key area that QML will excel in. Now, recent advancements in computing and sensing offer great potential for Alzheimer's disease innovation. Programs cut into fragments called dynamic circuits or circuit cutting. You run on multiple different smaller qubits of quantum computers instead of one big one. So quantum diamond sensing is making a lot of headlines too, and has early medical applications such as in vivo rat's heart with an order of magnitude better sensitivity, and then taking brain slices as well with that for sensing. Now, the FDA has been progressive towards conventional deep learning medical algorithms. So these are the ones that exist today. So there's been papers published basically to get them moving a little bit faster, but in the course of 2 years, there's deep learning medical image algorithms from GE and others that some weren't thinking that they were going to see because they're somewhat opaque and they're hard to evaluate. Now, for quantum, you're likely going to see new standards coming. For IEEE, quantum already has 9 of them, and then start to see these in potentially ISO, IEC, and NEMA for FDA submission, where FDA more focuses on the medical aspect, and then your requirements for hardware and software would come from other regulatory bodies. Now, the market opportunity for healthcare data, it is 30% of world's data volume and has a compound annual growth rate of 36%. And then you can also see that's through 2025, that's through RBC Capital Markets. And then imaging data in specific accounts for 90% of all healthcare data. It's a huge number. So over 5.5 billion global imaging procedures per year. And in specific, global AI medical imaging has a compound annual growth rate of 45.6% by 2027, with neurology or brain images accounting for the dominating share. Now, the product for ChemicalQDevice is stage 1, Alzheimer's prediction using existing imaging databases, develop these QML algorithms as the hardware progresses. And in specific, this is talking about if you have brain images that you have a healthy subject going to an Alzheimer's disease as reflective by the image of the MRI or say PET scan, or if you have mild cognitive impairment to Alzheimer's disease. And this is prospective to tertiary or if not more. Sometimes you'll look at a stable mild cognitive impairment compared to a progressive. So, typically there's a paper out there that it's binary classification. So, that will likely be improving. And then also to improve existing user satisfaction. This has basically go after the market that has the least amount of user satisfaction, and this would help with better accuracy. There's another paper that shows potential lower cost to run using quantum hybrid approaches. And then the big delighter is basically a lot of this will be improving over time as well. They're already installing one as we speak into Cleveland Clinic and IBM there. So the business model here is this: licensing, subscriptions, and partnerships. So licensing existing AI ML software's medical device buyers. I'll show you later the technical, how it looks, say, on the programming end. And this is basically, if you've heard of like a funnel or a flywheel. So flywheel is to turn prospects into customers, customers into promoters, and then eventually to scale. So this is where you have business investment growth over, or business growth over investment growth. Now, for subscriptions, this is established medical purchasers. And then partnerships, I took a Harvard Innovating in Healthcare course, and they said, look, look for companies and organizations that do good and do well, meaning do good in the healthcare aspect, and then do well financially. So the technology behind this is adapted from Sabayaji et al. And later this year, and it's basically you're starting on the left-hand side. So you need something to train from. So in this case, they used a different type of database, and prospectively, this is ChemicalQDevice would be ADNI, which is Alzheimer's disease neuroimaging initiative. So they're big into MRI, PET amyloid, and PET tau. And then you train from that. So basically these ResNet, this is classical. So this part, top part where it says pre-trained ML model, ResNet 34. It's very common. That's the ResNet 50, all these. Now in that you get a generic task because you're starting with generic data. And so that accounts for that top portion. Now in the green where it's a specific data set, this would be the patient MRI PET scans. And going in, and this is where it's starting to get into the hybrid of it. So fixed layers being classical and trainable being quantum. And there's a good number of papers with QML and imaging, binary classification. There's a multi-class classification with, say, for instance, COVID chest X-rays and a binary for Alzheimer's disease. And you see that your specific task using this hybrid approach gives you classification prediction. And then, so the kind of like the frameworks is PyTorch, and PennyLane is owned by a company. It's open source by Xanadu, which is a photonics hardware manufacturer, and it's quite popular with quantum machine learning. So on the right, you can see the real quantum computer on the top, and that's Qiskit is basically, as especially with dynamic circuits and running things on smaller quantum hardware, is you're going to see more of that. So we're going to see more of the real quantum computers, less of in proportion to simulators. Simulators are basically quantum programs. They're run on classical hardware, and it's basically the best thing that sometimes is the option. Now, I did the research on this, and basically I talked about this paper, the prediction paper in the lower left-hand corner, 2022 QML, and it's forecasting a healthy subject to AD, Alzheimer's disease. So a lot of these say basically will, or actually this is classification, but a lot of these, like the AI MLs, these 9 ones, it says, will the patient progress from, say, mild cognitive impairment to Alzheimer's disease using AI? So now we have quantum basically to insert in certain layers. And keep in mind, you'll keep classical with a lot of these. So the competition, they say it's a very broad field. So it could wind up that somebody's doing the same exact thing as ChemicalQDevice. Now, I arranged this by number of employees. So Meritive is Ann Arbor, Michigan-based company. Top 3 in class. It's a ranking system. They're in 9 of top 10 U.S. hospital partners. So just figure they're in the mix. So without going into exhaustive detail, they partner with other places too to get the algorithms. And then they also have people like hired on as employees that do it too. So Viz.ai, 390 employees. So these are just kind of highlights, 73% faster treatment decision. Now, what I wanted to highlight with all of these is basically they're often a specific disease that you're looking at. And the tendency as an industry is for CT scans, which is X-rays, which are faster, but you get some radiation with it, X-ray radiation with it. But especially with AI Doc in the upper right-hand corner at 370 employees, is they're primarily focused on ER. So instead of having all these radiologists sit down and look at images, is that it's doing that portion. So, but figured kind of like the things that are very time sensitive, so maybe less of the MRI and PET scan. So Rigetti Strangeworks is very important because this was announced this week is Rigetti is opening up their quantum computers for QML, and medical image classification is one of them. So as far as I know, this is kind of like the first big push in industry as far as in hardware, and then Strangeworks is more on the software. So figure you can lower parameters. There's certain things that just quantum does better. Now with Sirona, 70 employees and Radiology OS package, so they have some partnerships, 6 of the top 50s, and Analytic here saves less than 45 seconds per study. 47%, they found that 47% images need relevant data tied to it. And then the lower left is interesting, subtle medical. So basically, when you do anything in NMR or MRI, is the medical version of it, is you can do less scans or more scans. Now, more scans typically gives you clearer images, but this allows you to use the fast setting, meaning lower number of scans, but then their algorithm makes up for it. So they're saying a quarter amount at a time. And then they're using denoising, with basically they're not as fast as CT scans. So MRI and PET scans. Now, Behold.ai is basically, you've probably seen these things. One of their videos is actually quite interesting. I included the links here to the 73 and 74. Is basically a lot of chest x-rays. Now, a lot of times you'll see for CT, you can do brain hemorrhaging. And this is basically, wherever the area of being affected is in the middle is going to be red, and it kind of spreads out. And then here on it, I think they're Japanese-based, auto-quantitative Alzheimer's, so it gives you a bunch of stats on it. Very quite interesting and applicable to the startup. Now, and they're saying basically 97 brain segmentations, which is, I believe, a lot. So 15 employees right there. Now, the ask is this, is partnerships. So medical experts, quantum experts. On the medical side, existing AI, ML, neuroimaging algorithm experts, Alzheimer's disease prediction, brain image database experts, regulatory submissions, clinical approvals. Now, on the quantum side, QML, neuroimaging prediction, there's probably a bunch of people out there that does QML, medical imaging classification, and then that's the next step is, a little bit more expertise is needed, or, potentially more for prediction. And basically, you don't want big circuits, you can optimize them. And again, the IBM announcement of cutting up circuits, and I think other places do it too, is basically things run better. And this basically, so you have to know how to run in simulators, real hardware. I've run a circuit before on a simulator, and then kind of like the quirks with it. So say, for instance, your potential power is higher running on a real quantum computer, but your noise is also going to be higher, at least in the near term. Also doing accuracy validations, and it's very important to be proficient in documentation. There's lots of very talented people out there, but the phrase is if you get hit by a bus or win the lottery, can somebody replicate your work the next day? So here's a quote, good teams incorporate teamwork into their culture, creating the building blocks for success. Ted Sundquist. ChemicalQDevice is partnering with organizations that do good and well. I kind of touched on that a little bit before. Now, I want to do a big thank you to all these business programs I've been taking all year. So currently it's this BAPSIN, so Thriving Innovation, very good reference articles. So these are big companies, kind of frameworks, culture, those types of things. The Harvard, very interesting as well. I reached out to the professor. She's been at Harvard Business School for 50 plus years. And this is basically classifying. So you classify certain types of companies, based on their strengths. University of San Diego, lean business model and business diagrams. Then you have Maryland, product market fit, endurance scale, new business. So in previous decks, I've included, kind of details on how it relates to the startup here. Now, MIT, this is very interesting because many people think that your IP is sacred, and chances are in an early stage, anything like earlier than a year, or maybe even like a year and a half, is you really have to share everything. And they say, in order for rivals to replicate your work, they would have to have the skill, interest, time, and team. And you may get some of that as far as other companies, getting into that, but you're going to, in my opinion, benefit a lot more if you're open. Now, Stanford, this is basically getting into that Stanford culture, a bunch of good examples and quotes, and but I really enjoyed that program as well. Now, growth potential. So this is basically future studies, future work, these types of things, is stage 2. Okay. So I'm not going to touch too much on stage 3 and stage 4, because stage 3 is basically a combination of 1 and 2 between getting better prediction, better imaging, and stage 4 is more submissions for FDA. So in stage 2, it's about using quantum sensing, quantum computing to get better images to begin with. So raw data acquisition begins at the detector level. And quantum sensors, in specific, these diamond quantum sensors, you take diamond and then you make modifications to it, and then it's fluorescence on it. And then, so you're measuring the red light that comes off in the presence of some, say, magnetic or electric field. So that's very interesting, and I've done decks on that before too. So image formation quantum algorithms, these are reconstruction. Image computing quantum algorithms, these are segmentation, visualization, and the like. And also to improve user satisfaction with signal to noise ratio, sensitivity, resolution, performance. Now the benefit is better images, right? Is a lot of this technology is likely going to wind up in your next MRIs. I don't know the time frame, but that's where things are headed, where it makes sense, where you get better results with quantum. You'll see these hybrid approaches, and the lighter is things will get better with as the hardware gets better. So this is medical image processing. So this ties into ChemicalQDevice growth potential. So this is basically on the top 2 are image formation, and then the bottom ones are image computing. And there's all up and down, like, people think of like quantum as binary, as like you either have quantum or you have classical. But as you'll see, and I shared with the technology slide in the pitch, is basically there's certain aspects that you can run on a quantum computer for that specific task. And then at that same time, you're running classically. And keep in mind, Dell already has quantum solutions. So it's incorporating a technology called ion trap from IonQ. Now, this is in the specific. So in data acquisition, so a lot of these are diamond quantum sensors. Some of these it's called quantum image processing or quantum imaging, ghost imaging. It's, basically there's like multiple companies worth of opportunities here. And then in reconstruction, you'll hear a lot about reconstruction algorithms. There was already an MIT paper a couple years ago on the reconstruction algorithm for medical imaging. And, for medical, this could also be motion correction with somebody in an MRI that's moving around. And then if you have noise or artifacts, those types of things. Now, in the bottom part, the image computing, you have whole brain segmentation. Visualization is more something that I probably won't get into. And then management, you're talking quantum internet, quantum cybersecurity. I had mentioned some of these, the ones below where it says optimize quantum circuits is important. People have big papers on these, is taking a program like this and then reducing it. So we've gotten very creative as an industry in designing algorithms, circuits, these types of things, because the quantum hardware has not been awesome. But with NSF saying practical quantum computer next year, with IBM saying you can chop up the programs into fragments and then run them on smaller quantum computers. That might actually be like a bigger impact in the near term as far as going for millions of qubits, where IBM's recent is like 433. And then there's other things that you could do as far as generative adversarial networks on, quantum hardware. It's the quantum approach, and then radiomics automation and quantum federated learning is kind of a little bit down the road there. So for growth potential, the market opportunity is in drug trials. So when you have new Alzheimer's drugs, you need to validate, and they have all these procedures as far as a PET scan is required at time X, and then it's just specific to the manufacturer, the type of drug, all that type of stuff. And better brain image performance is desired. So this is where you have prospective imaging improvements in sensitivity, signal strength, and or resolution. So this is part of ChemicalQDevice stage 2 with emerging quantum algorithms and emerging quantum sensing. So it will take time for things to become standards, but kind of this is what it looks like the future will be. So I did this study. So this is the Psi, Roche, Lilly, and Anavex. The first 3 are ongoing studies. They're current. And then the last one, the Anavex, has ended. Now, as you can see, the participants is relatively high. And like I said, at different points of this, there's growth potential because of the dependency on MRI and PET scans. Now, they're typically slower. And then there's one of the companies I mentioned is they have an algorithm to kind of like do less number of scans with a quantum with their specific AI ML. So you could just see these certain things. So there's certain things that can exclude patients from getting an MRI if they have a metal fragment in their eye, say for instance, like from welding or like sanding. It's a big magnet, and then they might not qualify for the study. But basically, you'll see all along here, like for PET scan for Roche, change from baseline in brain amyloid load by amyloid PET and brain tau load by tau PET. So the 2 big things for PET scans are amyloid, which I'll show you in a graphic later, and then tau. So amyloid's more outside the neuron, and then tau's more inside. So yeah, basically, in my opinion, like based on the literature and everything, is just if you can get better neuro images from the get-go from quantum sensing, and even you'd have during that stage 2 with detection with better algorithms. There's machine learning algorithms that support quantum sensors. Is like I said, there's many opportunities for growth in my opinion. So in specific, the hot topic has been in medical imaging. So you have your Google Cloud, Amazon HealthLake, and then Nuance Communications and NVIDIA. And what this specific slide shows is that, the shift is being transferred from radiologists or neuroradiologists into AI and ML software. So you'll hear this phrase as far as like, we're here to help the radiologist. Amazon says overall the number of radiologists is decreasing. And it's basically, yes, that we will likely remain to have many radiologists, but maybe these cases where they say they have rooms of radiologists and they're like sifting through images and they can't keep up with the ER, stuff like that. Is basically, it's very good to see that this is mostly, if not all, conventional AI ML, and what the impact that quantum will have on the detection side, and especially on the it's QML at this point, quantum machine learning, process some of these and get better results and make it easier on hospital staff. Now, the growth potential can be seen in these 4 bullet points. So developments with existing image databases and quantum machine learning will present opportunities for Alzheimer's disease prediction improvements near term. Now, imaging processing steps with emerging quantum technologies can likely utilize to create better brain images. And where the rubber is really going to hit the road is in stage 3, is you already have, say, your prediction algorithms with quantum, and then, your better image images, with also algorithms and with sensing, that kind of like synergy right there between, with stage 3. And then in D is basically some things are going to happen, have to happen with regulatory. So we're talking ISO and ASTM, NEMA, IEC, those types. In order for those new quantum regulations to be accepted by FDA. FDA is more like medical, and then patient safety. So the ChemicalQDevice mission statement is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and/or resolution combined with advanced prediction and neuroradiology for Alzheimer's disease. This includes quantum sensing, algorithms, and computing with MRI, PET, and quantum machine learning neuroimaging techniques. Now, in this supplementary slide, so these are basically what's going on behind the scenes. So in order to incorporate quantum technologies into healthcare, basically what these are showing is the quantum computer and investments in quantum computing continuing to increase. So compounding annual growth rate, you'll usually see 30-35% for quantum computing in this study, that 166 reference. And then as you could see in 2020, only $683 million private investments. And then the next year, so last year, $3.2 billion was a big year. Now, Curica says global quantum efforts of $30 billion for this year. I think even IBM is $20 billion, just one company, but it's for other types of technologies, not just quantum. And then Boston Consulting Group says by 2040, there will be $850 billion annual value in quantum. So there's a bunch of driving forces. So these are the big companies. So IBM Cleveland Clinic is basically, they're building one right now. They have a 10-year partnership. NYU Langone, Hospital Fermilab, basically to get better MRI analysis. They're building quantum computer on their own and quantum sensors. So National Institute for Quantum Science and Tech, you have your, basically they're saying the diamond quantum sensors or quantum diamond sensors for increased MRI sensitivity. And then you have Mount Sinai Hospital. So you see Mount Sinai Hospital, NYU Langone, and Cleveland Clinic. They're progressive with the technology. Sandbox AQ is a Google spinoff, and it's for quantum security. And then the National Science Foundation next year, I don't know when, but they say 2023, we'll have some sort of a practical quantum computer. So it's interesting because a lot of these things are planned out. So in QML research papers, Amgen, IBM, IEEE, this is a big paper. It was electronic health records for rheumatoid arthritis, one of the largest QML studies. The Roche QC Ware paper for medical image classification, kind of like the stuff I've been talking about. And then cognitive computation, NIH, QML model, better than CML. And this is for COVID-19. There's at least 3 or 4 QML, quantum machine learning, COVID-19. So these are typically chest X-ray CT scans you're looking at. And then similarly for BMC and Springer Nature, that was kind of the big paper, that 178 source right there. Now, most of it, besides the Rigetti and StrangeWorks news from this week, focusing on medical imaging, similar to ChemicalQDevice, is in drug discovery. So most of these are like enzymes, approximating with quantum simulators as everybody waits for better hardware. And I've heard some progressive, I've had one of these CEOs on the discussion, and they say, they're doing things in specifics. So it's not like you can fully simulate caffeine and, all the receptors in a human body, with high efficacy and all these types of things. It's just very specific things that the pharmaceutical industry wants done. So this is the regulatory guidelines. So this is basically ISO, IEC, NEMA, ASTM, ANSI. And basically, if they don't know the IEEE quantum standards in hardware and software, internet and more, this is a good framework. Just because, there's a need for quantum computing, the first one with quantum bits. And the nature is different. So you need to run multiple shots. It's called to get a better answer. It's probabilistic. They're not bits like on off, like this is definitely your answer. It's more, like you have to average things. And then specify areas, quantum mechanics. So that's the whole key, is like many experiments have been run that didn't need to be run on, quantum computer, quantum simulator, because the conventional approach, just conventional, is either better today or will have advantage in 5 years as classical computing gets better as well. And then this is basically, I took the last 10 of the FDA AI ML submissions or approvals. And then as you can see, there's different regulations. So a portable MRI with post-processing requires, say, over 15 regulations. Whereas if you have something for pre-existing images, i.e., ChemicalQDevice stage 1, is that it's going to take a lot less. It's an algorithm. But nonetheless, there's different stages of algorithm, from locked all the way to continuously learning, like deep learning, which is harder. And then this is a good hardware overview. So the ones that I hear about and read about in literature is ion trap and superconducting qubits. So these are ion trap is IonQ and Quantinuum. And then IBM and Google are the superconducting qubits. But in all these, the biggest news is this dynamic circuit. So you can see under IBM, is that cutting programs, these quantum circuits, into pieces and running the fragments on individual smaller quantum computers has big upside. So there's an HPC Wire article that basically said, even though IBM searches for millions of qubits and people want millions of qubits, that we could do a lot with, say, having a big circuit and then cutting it into pieces. Now, in order to visualize this, so this slide kind of goes together with that technology slide in the pitch deck, is that there's certain parts. So say, for instance, this is a binary classification using quantum machine learning and conventional approaches. So starting at the top, you have a classical layer, and then the next step is a quantum variational circuit that's run on a quantum device. And I believe they ran Penny Lane, a quantum simulator, and then it goes back to a classical layer. And then after that, you have your classification of demented or not non-demented for Alzheimer's disease. So it's just interesting because, these qubits, this is only 4 qubits here. So Q0, 1, 2, 3, and that's not a big circuit at all. So a lot of these are just basically using their approach is, I think it was 92% if they just did everything classically, and then they got 97% classification accuracy. So these are based on existing databases and accuracy, basically, is that it seemed to be a productive study. And then I had reviewed this paper before in previous decks, and then also a medical doctor forwarded this to me as well. So it's a lot of good, like, these early papers, the fault here is the quantum simulator. And then, we're still kind of waiting, late 2022, especially early 2023, is so you may get a tertiary classification. So meaning a healthy subject, mild cognitive impairment, and then AD. And then, so here's what's going on in the brain. So when you see, especially these drug trials, when they say, like, we need a tau PET, or we need a amyloid PET scan. So the tau is typically, you have extracellular, and then, goes in, and then it releases again. And then the amyloid beta, say, for instance, these drugs, the Alzheimer's drugs, are typically addressing amyloid beta. And one of the more recent one, it wasn't exactly that, but anyways, in PET scans, it's going from amyloid beta to tau. And then here's a bunch of the Alzheimer's organizations to support. I've done advocacy for Alzheimer's Association, and they all have different objectives, but definitely worth checking out. Because, caretakers, their families have a hard time with this, and basically to get better prediction, better imaging or brain scans can help out. And then here's a bunch of the references. So I think it's I'm going to scroll through here. So 222. And then I'd be interested to see, I think we're getting more medical people. And let's see. So you should be able to chat. And then you can come on, Good to see some familiar faces here. And I know some people on are quite into quantum, if not medical. But David or Hannah, do you have anything?
Yes, I actually I do. So I was really interested in your the presentation, especially in stage one, that you're saying that you're currently doing predictions for classification of AD. Is that correct?
It's just literature, so I'm following literature at this point.
Okay, okay, yeah. Okay. And the classification, is it based on literature which was given for example, so standard neurological understanding of, like, for example, classification of synapse degradation? Is that something that is?
Yeah, my understanding is that the Alzheimer's disease neuroimaging database, ADNI, or initiative, is they already know what the images are. So if the patient really truly is demented or not demented, or say even like a quaternary would be mild cognitive impairment, stable mild cognitive impairment, progressive. And then so it's blind to the researcher. And then, so like I said, with this, one of the more recent slides is that they're running just a conventional approach, and then versus their quantum approach, and that's the whole 92 versus 97%. But yeah, it's all for most of these papers, and I listed kind of, so there's at least 9 recent, the 2021 papers, AI ML for prediction. And then so they predict typically from MCI to AD. And as the studies say over the past couple decades have gotten better, is that, with deep learning, is that accuracy improves, those types of things. But yeah, that's my take on it, is that they have the answers, and basically you get the set, and you could run simple images. There's many other types of image databases, but basically your accuracy is compared to what they believe what the true answer was.
Right, I see. Okay, that makes sense. Yes, okay. Yeah, that clears it up. Thank you.
Yeah, you're welcome. And then David, do you have anything?
Yeah, I'm just curious. I mean, now the quantum is so small, they only have few qubits, right? I have looked at PatternName. How they improve with the 4 qubits? They improve the accuracy from 95, 97. How that works?
Well, that specific study was run on a quantum simulator. So this is, using PennyLane, and then so PennyLane is known for QML. And yeah, so that, I think that specific one was 4 qubits. And it's interesting because I think simulator has improved as well. Obviously not exponentially like what's potential for the quantum hardware, but I don't think they used any circuit cutting or anything. But in all these papers, I haven't come across anything. Say the IBM Amgen paper was, I think, a 22 or 27 qubit.
Did you mention? Did you give a number? Did you say accuracy from 95? What's the number from improvement?
Yeah, so they were claiming, and then I'm going to post the deck too. So it's got you can look at that specific slide. So they were claiming. So it's always good to run something against your own experiment you're trying to do well. So meaning that the 92% classification accuracy for demented and non-demented versus if that quantum hybrid approach with the simulators, 97%. And these things will work out because this is an early paper. And then
I'm kind of curious, how do you, I'm doing the quantum machine learning. I also went to the PatternName, the code camp. So I'm like, how the 4 qubits can improve that much, like almost like 5%, right? Accuracy.
Yeah, I know for 2 you don't get much. For 3 is when you start to talk about, there's, because of entanglement and multi-qubits and that kind of effect. So it's just interesting because there's been a number of papers with ion trap technologies that they have a better circuit connectivity than, say, superconducting qubits, and they tend to make Nature articles better. So the recent paper for that, I think it's like polymer characteristics, but it seemed like it was the most like state of the art paper using using a real ion trap computer. So yeah, I think it exists that running simulators with small number of qubits, like 4, that other organizations and authors have posted advantage. So now is the question is like, how good is the advantage? And
it's pretty good, right? From the 5% more is exciting, right? I mean,
yeah, because even for those that don't know, there's another technology that's been around for 2000. It's called quantum annealing, and it's only for specific types of problems called optimization problems.
Yeah.
And then that one, I'd see boosts of 3 or 4%. And then other people that came on the panel would say similar types of things as far as like, that can be a huge thing. If you're in the 90s, 92 to 95 or 92, 97, is depending on the application, if you're spending millions of dollars or lots of electricity, those types of things, that it's of use. So I think the biggest thing when they say that we haven't had quantum advantage is that it's the exponential, because Lockheed Martin bought the first quantum annealer in 2011 for $10 million. And then, you continue to see it. It's, GE, who's it, like Toyota for like spring dampening, those types of things. So there's been applications. So what I commented on a little bit earlier in the discussion is basically the computing hardware is not awesome yet. And we've gotten so creative as far as taking a quantum circuit, a quantum program, and reducing it to a certain point just to get it to run somehow on some quantum simulator or hardware to get advantage. So I think that plays to us is basically, if this NSF practical quantum computer for next year, if it's a significant boost, we have that framework, and we can cut circuits into pieces with dynamic circuits like IBM. And I think there's a lot to look forward to here, because these QML papers, say the last year and a half, there's been a number of them, and big, Roche, and then Amgen and IBM, and then there's been like 4 COVID. Now they couldn't get the COVID I'm not quite sure why it didn't go clinical, but basically figure a lot of these are laying the framework as the technology gets better. And it just seems like there's a number of things working for anybody that wants to get into a quantum application now.
Have you looked at the Q-Arrow computer yet?
It's gate-based superconducting, right?
So the Q-Arrow is use the neutral atoms. The one in Boston, Q-Arrow.
I don't come I read a lot of literature. Last week I think I did 4 or 6 papers, and I don't come across neutral atom. I've reached out and I've got a call.
Like a Q-Arrow, just make available. They're going to have 256 atoms available. It's brand new. They make available through Amazon Bracket a couple weeks ago.
Oh yeah, So we talked about, I think, 4 different hardware technologies. We haven't talked about photonics. So, and then quantum annealing. So that's most of them. So basically, as far as I heard, so Russ Fine, David. So Russ put together a hardware map as far as like all of the, and then one of the slides I put one in too, but his is kind of like, it covers a lot more.
Yeah, I got his picture in my LinkedIn link. Yeah,
it was nice. Yeah, and awesome question. We can come back to David. Baketama or Tom, do you have anything? Feel free to unmute. Go ahead, Tom. We can hear you a little bit.
Okay. Yeah, I think I need to switch my other microphone. Nothing right now.
Okay. Yeah, so it's exciting time. To David, I could talk all day. I just want to see if anybody else had anything. And then Hannah, if you have anything.
Yeah, I did actually have something. So for the quantum error correction, so I was looking a little bit at some literature, and from what I can see, based on sort of the quantum error correction that we have currently, I'm just interested in how that classification of error correction it works with classical, so MRI standard sort of noise. You know, if you were to have an image come through from a classical, you know, classical image set or MNIST data set, the current error correction that we have, do you know if that is something that would have to sort of adapt to, like, based on where we're at this point? Do you think that we would have to kind of advance that field more before we get sort of more of those clearer images that you were talking about?
Well, I'll start off with this: is the original classical computers had error correction issues. They had issues with gamma cosmic rays, and that's the same thing that quantum is experiencing right now. Now, they have a clear distinction between error mitigation and error suppression. There's a really good paper, I didn't include it on this deck, but it's from Chinese researchers, almost 500 sources. So even IBM has mentioned this too, is you can have algorithms to account for some of the error, but true error correction, if you look at the IBM roadmap, where it's kind of hazy because they put it over it and there's like a block that extends left, so it might come before. True error correction is maybe 2026, and then we're in the noisy intermediate scale, quantum, the NIST, and then I think the next one is like partial error correction. But basically, with the circuit cutting, dynamic circuits, is that even if you have this, now it's better to run on lower qubits due to error because the effect is not quite as large, and you have these other things called like Bain plateaus. So what it seems like is mostly mitigation and suppression. One, I know, so the algorithms consume resources to fight against things. And and this goes back to the craftiness of without having awesome quantum hardware, is basically there's certain types of circuits and programs and all these types of things that are a lot less, say, susceptible to barren plateaus and error and these types of things. And I've come across papers where it just, you know, where it says, you know, this is not, so a barren plateau is basically, you know, there's an IBM kind of cute picture of it. You have like a forest, and then basically that forest shrinks down, and then you can't do your, you know, quantum calculations with higher number of qubits. So I think it was last week or the week before I came across a paper, and they said basically this negates a lot of that barren plateaus and local minimums that quantum is susceptible to.
I see. Okay. Right. Okay. So probably 2026. Yeah. I mean, that seems likely, because I'm based on my experience in quantum error correction codes, and especially topological error correction is something that is pertaining to a lot of research as well. But again, that may not sort of necessarily coincide with you know, annealing or gate based, but yeah, that's kind of what I wanted to.
Yeah, and keep in mind with all these things, it's not always the technology that's theoretically the best. So theoretically the best is typically gate-based superconducting. It's the one that will scale. So yeah, it's interesting because IonQ Quantinium, they're getting more of like these applications. So the, you know, with Dell, with IonQ, and then they just had something recent that was, you know, it's just applicable. And same thing with quantum annealing, applicable, but the fan base and the push behind getting superconducting qubits to work, because it's what most people learn about in university, is enormous because of Qiskit. And IBM's putting, you know, now $20 billion, not just in quantum, other technologies. And then President Biden's up in New York last month or October, and there's a picture of him with IBM CEO next to a quantum computer, a gate-based superconducting quantum computer with an American flag in the background. So the push is definitely there, right? And I think I was alluding to Russ Fine's article, is basically he doesn't expect too many other types of hardware technology, although there's, you know, there's more. but I think the 5 or 6 that we have, so gate-based superconducting qubit, ion trap, photonic, neutral atom, annealing, and spin qubit. I think those might be it.
You forget diamond.
Yeah. So
Yeah.
yeah, diamond quantum sensors can be used as
No, diamond. What's called diamond NCV. Something like, I don't really.
Well, yeah, that's nitrogen vacancy. So
yeah, that's right.
I've seen that in computing, and I haven't heard about it too much in computing. You'll hear about a ton in quantum sensing.
Yeah.
Anyway, it's kind of good because, you know, we're talking applications now. So for chemical Q device prediction, and now better neural images, and those neural images could wind up in, you know, they say we need to have quantum standards now, and we need these better quality images in order to have, you know, better research. So yeah, that's where it seems like a lot of these things, because, you know, there's some early applications, and, you know, there's Fidelity and Goldman Sachs and Wells Fargo, you know, and there was really early papers, say in 2020, 2021 with financing, just thinking that they can have this average or below average quantum computer at that time compared to today. And anyway, they're learning lessons, and you have to start somewhere. So
yeah, that's true. Okay.
Now, I guess for the hybrid, you don't really need accuracy. Even the error is okay, because what happens, you part of the calculated by the quantum, most of them can correct by your classic machine learning. So basically, you don't really care much accuracy about the quantum. I mean, this errors is okay because.
Yeah, and that's totally right. You know, it just depends on the what you're trying to do, and they say quantum advantage or quantum supremacy is over today's best classical, but they might want to push that out to like 5 years, like what we project classical. But I think in all these things, because if you look at NVIDIA, there's hybrids, right? So CPU, GPU, now QPU, and then one of the previous, or one of the attendees that comes usually is basically they'll talk about the power of GPUs and running quantum mechanics on GPUs. So there's going to be a lot out there. So it'll be interesting. I think the biggest thing is focus is like, can you get the results? Can you validate them? You know, these types of things. And AWS bracket keeps, I think they're up to 5 or 6 different. You had mentioned that, David, with a Q arrow.
They have a Q arrow already there.
Yeah, so, you know, I don't hear too much about Azure or Google, but Google is the wild card. Now, for those that don't know, Google had quantum supremacy back in October 2019. Now, that quantum computer called Sycamore has not been updated yet in public. However, they've been doing this crafty thing. So it's a science paper of June of this year, and it extends from an archive from last December. So basically, they use quantum sensing and quantum memory to basically extend the effects and mitigate the noise. So using quantum machine learning with these other quantum technologies, you can hold on and store something, and in the weird quantum world that you have better effect holding on it and storing it as opposed to classical measuring it right away. So there was a Harvard paper, I think last month, and maybe even I think it was early last month, and they have 2 seconds of quantum memory, and that's done with a diamond, David. So they took it's called silicon vacancy, and they used it for communications. But you're going to see this interplay of making quantum computers better with something that was, you know, currently published for, say, for instance, internet, quantum internet. But that paper right there, the silicon vacancy instead of nitrogen vacancy, and there's different quantum effects tied with that, is basically you could start to see huge bumps, you know, based on what they're reporting with an old quantum computer. So basically that 2019 Sycamore in this paper in 2022 in Science, they redeemed it with the quantum memory and quantum sensing, so that the quantum effect, with sensing memory computer was greater than the noise. So there's all these little tricks going on, and for me, I got into this, say, 2021, increasingly, and you're never 100% sure, but now it just feels like, yeah, I'm just ready to run. This is just, it's a normal program tactic, right? So it's not like if quantum will happen, it's just like, okay, yeah, the hardware is getting better, but I can still, draft up experiments and then, have my application basically. And then anybody else that we haven't heard from, you can go ahead. I saw somebody else join there. Appreciate everybody coming on. And anything else? So the things to look forward to in 2022 is the NSF Practical Quantum Computer, IBM. So that 433 qubit processor that we heard about this year, that they say is modular using dynamic circuits or circuit cutting to over 16,000 qubits by the end of 2023. So I'm telling you, it's all in these, because if you can cut circuits apart, your requirements for, number one, high qubits and low error are significantly relaxed. So that's typically the issue is, yes, we still want over 1 million qubits, but at that same time is like what, the barren plateaus, local minimums, and the error, compounds itself. So, so the reason why people are, especially people that have gone to university and studied this, is in many cases, so if you have 50 compared to, say, 51 bits, you're linear in your growth. Now, 50 compared to 51 qubits is exponential because your information doubles every time you add a qubit. So this isn't a perfect system. And say, for instance, the one that kind of reminds me of that the most is ion trap. And especially with ion trap, you can connect this qubit compared to 10. It's called all-to-all connectivity, but with gate-based superconducting, it's just nearest neighbor currently. So I would talk to the manufacturers, and they said they run some programs on real quantum or gate-based superconducting qubits, and then some on ion trap. And say, for instance, I think I was watching a Quantinium podcast, and it says it's 10,000 times slower, ion trap is, than gate-based superconducting, but its coherence is 500,000 times better than superconducting, plus it has all-to-all. So it'll be interesting because we haven't talked much about the photonics, and everybody wants photonics to work because it's room temperature. Now, IBM or Google, the Rigetti, there's this like figure really cold, and then ion trap, I think it's just local cooling. Now with photonics, the 3 Nobel Prize winners were all based on quantum and photonics. So it's interesting because Xanadu had this big paper June 1st of this year, and they claimed that they ran something in, say, 36 microseconds that would have taken 9,000 years. And that's promising. And you see these similar types of things with Google Quantum Supremacy back in 2019. So anyway, they're not like practical quantum computers. It's like a specific task. So.
Yeah, actually, I keep track of all the photonic quantum computing company now. I have like 6 of them top. If you look at my LinkedIn website, is my featured report about like 6 top quantum photonic quantum computing companies.
Oh, okay.
There's Xanadu. There's one there's a couple in the Europe. Like there's called QX Quantum. QUIX Quantum. They got it from the German Air Force or German space something gives the $40 million to them create a general universal quantum computer based on photonics.
Yeah, it's interesting. I don't know if you could run Xanadu's photonic. I know Xandu's.
No, Xanadu is not general, it's not universal quantum computer yet. They're behind. Actually, if you go look at QUX quantum, QUIX quantum, they're pretty ahead of them.
Yeah, it's interesting because I mean, say I joined a podcast maybe like 9 months ago, and they said the biggest push was to use less of the custom-made photonics parts and more off the shelf, because things just, they couldn't control the whole thing. But you know, you try to get results, you know, like any experiment, just do whatever works. But then that's what they said, is kind of like they're limiting themselves to, you know, kind of like the readily available parts.
Yeah, you have basically have integrate them, because if you use the parts off shelf, it's not going to work, because it's not going to come together. Another company will be a Psi Quantum, right? Really popular in the, that's a huge one.
Yeah. So, I mean, geographically, that Bay Area has at least 6 quantum companies, either hardware, software, anywhere from QCware. I don't know if did you go to Q2B this year?
No, I didn't go there. I know people who went there. I know the yeah, so they're getting popular. I mean, Psi Quantum, they have like a $250 million investment. they're already unicorn now.
Yeah, I saw that too.
Yeah.
And it'll be interesting, but like I said, as far as experiments being run in the public, well, I'll have to rethink that, because on AWS Braket, I think you can run Xanadu's photonics on there.
Yeah, but it's not universal quantum computer yet. It just, you can run different things, but really limited.
Oh, okay.
Actually, I'm looking into there's something called this. What happened? There's a beetle fan, right? So there's a panel name that now is another called the strawberry fields. That's a quantum program. Yeah, it's interesting. Yeah.
What all are the universal quantum computer hardware right now?
They're not ready yet. They do have general gates-based quantum computer. If you look at if you go back to the QIX quantum, they're pretty detailed. They have papers. QUIX.
Yeah, and I guess for everybody else listening in, is that as far as good resources, I don't know where you are in your quantum journey, but I did it was like a 235 source reference timeline from the early 1900s, and it was one of the hardest things I ever did, because I had.
Do you have I can ask you link, right? I ask you link from the LinkedIn. Yeah, I ask you if you have the resource.
Yeah, but I think to anybody, that's a great start, because it combines everything. There's a football player from Yale that switched to quantum. It says from football to quantum. You know, but not just that, but like the big ones too. So, you know, the Xanadu announcement June 1st, and anyway, so that I ended it in June, and then I've been strictly kind of incorporating medical or quantum into medical ever since, and doing those decks. But yeah, as far as, because it sounds like some people may be medical here, but you know, feel free to put in the chat if you don't want to come on, and then you know, feel free to answer questions. But I really focus in on the medical quantum now, because I started off with reports, and then it's just everything's open source now, and then I get some pretty big companies looking at my pages. So, you know, we'll see. But basically, many big companies, they want to make pushes into healthcare. These are huge companies that we're familiar with, and you've seen from those compounding annual growth rates that, you know, usually healthcare data is over 30% of all data that exists, and it needs to be protected, you know, secured, patient safety, all that kind of stuff. So there's all these rules that, you know, and especially with AI ML being updated, and now it's like, you know, incorporating certain parts of quantum into it. So anyways, I think the push is there as far as the quantum going.
The Kevin is a healthcare really conservative, right? It takes long time to have anything getting the healthcare, right?
I compare it. So the FDA AI ML. So there was a paper out that basically said in 2020 that it's a petition for them to start accepting it. And to greater detail, because I've done other kind of like bar charts that show even back in, the 90s that there was some form of AI that snuck in. But AI, ML, and FDA, I think it's been like maybe the past 4 years. And the biggest issue is people really want this continuously learning, deep learning kind of stuff, like neural nets, and that finally caught on. So the last 10 that I looked at least 2 of them use deep learning, and this is like GE and somebody else. But deep learning is a highly complex thing that you don't necessarily know what's going on all the time.
Yeah, so it's hard to get proof, right? You cannot even trust them. Even the accuracy is right, but you cannot trust them. So they're not. So FDA say, how do you trust them? That's a problem.
Well, for me, the biggest thing is like, I don't think it's going to be FDA monitoring quantum hardware and software. It's going to be like the ISO, IEC, NEMA, that, because ISO, I think they do the continuously learning, deep learning part. And, you have to satisfy those conditions in order to for submission in FDA. So it'll be interesting because the biggest kind of like thing right now is like there's multiple types of hardware technology. And at that same time, we have simulators, and some papers say, they got better, reports, low qubits, simulators, and then without having this awesome hardware now. So, I think things will have to adjust.
I guess for the healthcare, they make sure it's ethic and also make sure it's extendable. So the explainable is really important. So you can explain results. Now deep learning, you cannot explain that, right? So that's right. But like human can say, oh, human doctor, right? Say, I have this one because of the reason. But deep learning, they cannot tell you why they give a result, right? So the explainable AI is really important for healthcare.
Yeah, they operate on principles. So for instance, there's probable benefit over probable risk. So there's probable risk in today's AI, ML. There's some uncertainty because of, training and bias and all these types of things in the data sets. And then the thing to get, so there's only been 510K approvals. So 510K approval means that your device is substantially equivalent to a predicate device or a pre-existing device that does similar types of things. Now, there's always ways around. I mean, with quantum, it's going to have to settle. But one of the submissions I saw had a predicate device and a standard reference. In addition, maybe there was some uncertainty because one of the, the feature set on their, DL or AI, ML, that type of thing too. But yeah, it's definitely, that's where I started kind of, is basically review what's required at the top and then work your way back. Well, anybody else? Any other last questions or comments? And then if not, so there's a bunch of references if you want more. David said he has some on his site as far as like those 6 new photonics. You'll find all kinds of stuff on mine, mostly healthcare and quantum on mine. And then if not, this is episode 61. This is December 15th in the middle of the month. Hoping you all have a good rest of the month and a happy holidays.
Happy holidays. Yeah. Thank you, Kevin. Bye.
All right. Take care.
Thank you, Kevin. Take care.
Have holidays. Happy New Year.